In this lesson, we're going to be looking at simplifying radicals. Now, in order to talk about simplifying radicals, we've got to talk about what rules are involved in order to do so. Now, this lesson, I do want to point out, is probably the most important in the unit. It doesn't mean it's the hardest in the unit, but it's the most important in the unit because basically what we're going to be doing here is we're going to be taking things like the square root of 50 and saying, can I write this in a better way that has less inside the radical and more outside the radical? What we're doing is very analogous to simplifying fractions. So when you simplify fractions, you're trying to say, hey, let's make as little in the fraction as possible. Instead of having 6/8, you'd rather write that as 3/4. That's really important in fraction work for the same reasons that simplifying radicals is going to be important. Anytime that you do a fraction problem and you get a fraction answer, in the end you say, can I simplify this? The same is going to be true for radicals. Every time we do a radical problem and we get a radical answer, we're going to say, can I simplify this radical further? Now, also in dealing with fractions, in order to find a common denominator, you kind of unsimplify. And we're going to have similar strategies that we use when it comes to radicals. So let's look at some of the rules that are involved here. Now, we had a rule of exponents that was the power over a product rule that said if I have a times b and I raise it to the nth power, I may as well have just raised the a to the nth power and the b to the nth power. Now, this is true whether that power, that n, is a fraction or not. So we could have a times b to the 1 over n and take each of those to the 1 over n power instead. Now remember that the 1 over n power means the nth root, or a radical. So in terms of radicals, this tells us if I have the nth root of a times b, I can take the nth root of a and the nth root of b. And that's actually what we call the product rule for radicals. So the product rule of radicals tells us if I have a product inside a radical, I could rewrite that as the product of each individual radical. So let's look at some examples that uses the product rule for radicals. Now I do want to point out that the product rule for radicals works both directions. So we wrote it as, I'll go ahead and rewrite it here. We wrote it as the nth root of a times b equals the nth root of a times the nth root of b. When we simplify radicals, we're going to be working left to right. But we can also work right to left. If you have two radicals that you're multiplying together that have the same index, you can go ahead and combine them as a single radical. And that's what we're going to do in this example. We're going to say if I have square root of 3 times square root of 5, that's the same thing as the square root of 3 times 5. And 3 times 5 is 15. So that's the square root of 15. Now we can involve a variable into the mix too, that if I have the square root of 21 times the square root of x, I could rewrite that as the square root of 21x. That's fine. Now sometimes we're going to simplify in the end. If we had cube roots, same thing applies. I can take cube root 4 times cube root 2 to get cube root 8. But then we could simplify this and say, hey, I know what the cube root of 8 is. It's 2. So these are examples of using the product rule for radicals from right to left when we start with two different radicals and combine them to a single radical. Now we will go the other direction as well, and that's actually what simplifying is going to be about. But I just wanted to get you some practice in using this rule first. Now, similar to the product rule for radicals, we could also come up with a quotient rule for radicals. And it's very similar. It's very much what you'd hopefully expect, that if we had a radical that had a fraction in it, that we could take the radical of the top and the radical of the bottom separate. And we've actually already seen this. So I just want to point out that it is a rule, and this is another rule that could go left to right or right to left. That this quotient rule, and be aware of what it's called because this does come up, that the quotient rule can mean if you have a radical of a fraction to rewrite it as a radical on the top, radical on the bottom. It can also mean the other way around. If you have a radical on the top and the bottom that have the same index, then you can go ahead and write it as a single radical. So let's go ahead and look at an example that utilizes this rule. Now, each of the problems in this example have a radical of a fraction, and directions on this would be something along the lines of use the quotient rule to simplify. And so if we're going to use the quotient rule tells us we can rewrite this as the square root of 25 over the square root of 49, which is simply 5 over 7. And we've really already taken square roots of fractions. We're just sort of explicitly saying now that this rule is okay. If we do the same thing to the second problem in this example, then we're going to have the square root of x on the top and the square root of 9 on the bottom. Now we don't know what the square root of x is, so we're going to have to leave that in the top. But as far as the bottom, we do know what the square root of 9 is, which is 3. And I want to include this example to point that out, that we could start off with a fraction and be able to take the square root of one of them and not the other, and that's perfectly fine. And so we get an answer that has a radical in the top, but not in the bottom. And that's okay. We can also move this up to cube roots. So the same thing's going to apply, that we can take the cube root of the top and the cube root of the bottom separately. And as expected then, cube root of 8 we know is 2, cube root 27 we know is 3, and we get a value. And we could press forward and do the same thing with a fifth root. We could write this as the fifth root of 3. Now on the bottom we could take the fifth root of all of that, but also remember though that we had the product rule that says I can take the fifth root of the 32 and the fifth root of the x to the fifth separately as well. Now up top, the fifth root of 3, we don't know. The fifth root of 32, if we look to our powers chart, is just 2. And the fifth root of x to the fifth is just x. And so remember that once you take a radical, the radical sign goes away. So we took the fifth root of x to the fifth, no more radical, it's just x. So now let's get into the really important piece of this entire lesson, simplifying radicals. Now, earlier I mentioned the example square root 50, and that's going to be a nice simple example we can take a look at. We can sort of figure out what we're doing to simplify and come up with a process or a set of rules that goes around that so we can apply it to more complicated situations. So if I want to look at square root 50, what I want to do is I want to use the product rule to rewrite this as a product of radicals. So the square root of 50 I'm thinking about as the square root of 25 times 2, so that I could use the product rule to rewrite it as the square root of 25 times the square root of 2. Now the square root of 25, I know the answer to that. That's 5. But then the square root of 2 doesn't simplify at all. It just copies down from step to step. And so to simplify the square root of 50, it goes down to 5 times the square root of 2. Now, there's the answer, but we haven't really got into what we did or why we did it. So let me just throw out another possibility here. What if I rewrote the square root of 50 as the square root of 5 times 10? So that was square root 5 times square root 10. Well, at this point, I kind of got to stop. I can't really do any better than that, and that's not good. That's not as nice as what I had over there as 5 root 2. And the beauty of 5 root 2, and really what we're looking for here when we're trying to simplify radicals, is we want as little left in the radical as possible. So, I don't want to just break it up randomly as 5 times 10 is just some numbers. When I break up square root 50, I actually broke it up in a smart way. By choosing 25, 25 was a perfect square. It was a value that I knew I could take the square root of. And that way, it will simplify. It will no longer be a square root. So you'll see we have 3 steps written down here. And these 3 steps are written out in a simple way so you can remember them. But we're going to get into the specifics of them as we start to move through different examples and this little introduction here. But as far as memorizing the steps, I want you to memorize them for simplifying radicals as break it up, take the radical, clean it up. Now, in the break it up step, we were really careful that we chose the 25 times 2 and we didn't choose 5 times 10. Why did we choose that? We chose that because 25 was a perfect square. I was looking for a perfect square and whatever is left. Most importantly, I was looking for the biggest perfect square that evenly went into 50 and whatever factor was left. So as you're trying to break it up, what I don't want you to say is I don't want you to say what two numbers multiply to equal 50. That's not what I want. What I want you to say is which perfect square divides evenly into 50. So not even what perfect square times something. We can figure out what the times something is. We just want to say what perfect square divides evenly into this number. That's what we want to look at when we're simplifying a square root. Now, if we were trying to simplify a cube root, then the correct question there would be what perfect cube divides evenly into this? And that's where your power chart's going to come in handy. You're going to look at your power chart and you're going to work right up it. You're going to say, all right, well, 27 is a perfect cube. Does this divide in? 8's a perfect cube. Does it divide in? So we're not going to say what two numbers multiply together to equal this. That's the wrong question. The right question is, which perfect square divides evenly in? Or in the case of a cube root, which perfect cube divides in? So we're looking for perfect powers to break up these radicals with. That way we can actually take the radical. So let's do some examples that just have numbers in them. Now the first example that we're looking at with the square root of 24, it's a square root. So because it's a square root, the correct question we want to ask is what perfect square divides evenly into 24? So if we look at our square table, our powers table, 25 is already too big, so we don't care about 25, so we move up to the next one, which is 16. 16 doesn't divide evenly into 24, and so we move up to the next one, which is 9. 9 doesn't divide evenly into 24, so we move up to the next one, which is 4. 4 does divide evenly in, and how many times does 4 go in? It goes in 6 times. So I can break up square root of 24 as square root 4 times square root 6. So remember your steps were break it up, take the radical, clean it up. So now in this step, we're going to say, let's take the radical. I know the square root of 4 is 2. Square root of 6 doesn't simplify any further. Now in this case, there's not really a clean it up step. Clean it up is going to come in some of our more complicated situations. But our answer here is just simply 2 times the square root of 6. And we can write that as 2 root 6. Now for the second part of this example, the cube root of 24, we're looking for a cube root, and so we're looking for perfect cubes that divide evenly into 24. 27 is already too big, and so the next perfect cube is 8. And 8 does divide evenly in, so we can rewrite this as the cube root of 8 times the cube root of 3. Now the cube root of 8, we know the answer to that, that's 2. But cube root of 3, we can't simplify any further. And so that's really as good as we can get. Now it is important to use these 3 steps separately. Don't try to combine them. And I'll tell you why. You might think that you can do it in your head. But I will tell you from my decades plus of experience in teaching this class, and I teach this class pretty much every semester, the most errors I see is when people try to combine steps in this, and that's because you confuse your own brain. If we do the break it up step every time, and that's all we do is the first step, then we're going to have nothing but radicals in that step. In the next step after that, we're going to take the radical. So the only thing we're going to change is if we're taking the square root of a perfect square or the cube root of a perfect cube. If we change it, we know the radical goes away. And that's actually where I see the most errors happen. Is when people start combining steps, I see crazy things like turning this into 8 cube root 3. Or when they take the cube root of 8, I see cube root 8, or sorry, cube root 2, cube root 3, because in their head, they're taking the cube root of 8, but they're leaving the cube root symbol there. Those are the types of errors I see that are obviously wrong, but if we always follow the same steps, we're not going to make those kinds of errors. If we always follow the same steps that say, in my first step, everything's got a radical. In the next step, things that change no longer have a radical. And then in the third step, we're just going to clean it up if needed. All right? So on to the last example here, within example 3. We've got a fourth root. Fourth root of 32, so we're looking at our perfect powers of 4. 16 is a perfect power of 4, and so that's how we're going to break it up. We're going to have the fourth root of 16, and 16 times 2 would get me back to 32. And then the fourth root of 16 is 2. I'm left with fourth root of 2, and there's my answer. Now this set of examples is going to include some variables and numbers together. Now the trick here, as we're trying to simplify these radicals, is basically just to treat them separate. Handle the numbers and handle each variable independently. So let's start off with the square root of 25 x cubed. Now let's start off with the break it up step. Even though you can probably look at this and say, I know the square root of 25 is 5, that's not part of the break it up step. That's part of the take the radical step. In the break it up step, we're breaking this up as perfect squares and whatever's left. Since the square root of 25 is a perfect square, just write it as such. But now we need to break up x cubed. Now x cubed, we need to break it up as a perfect square and whatever's left. So I'm going to break it up as x squared and x. That would get me x cubed, and I've broken it up as x squared and x. Now is the take the radical step. The square root of 25 is 5. The square root of x squared is x. And square root of x just copies down. So now in the clean it up step, this is 5x root x. Now I do want to talk about one other quick example just to point out because variables can get a little bit tricky. So let me just talk about a variable problem real quick. Suppose I had the square root of x to the 11th that I wanted to simplify. And I want to break this up as a perfect square and whatever's left. Now one of the errors I see people make when doing this is I see people write x to the 9th x squared because 9 is a perfect square. Well, 9 is a perfect square, but x to the 9th is not a perfect square. So this is not what you want to do. If we're talking about a perfect square with x to a power, even powers are perfect squares. So what I'm really looking for is I'm looking for the biggest even power that's less than 11. That would be x to the 10th. And what's left is x to the 1st. And this gets into something we covered last lesson because what is the square root of x to the 10th? It's x to the 5th. And you remember you can think about this with rational exponents because the square root of x to the 10th would be x to the 10 over 2, which is 5. And then the square root of x would just copy down. So when we're doing the break it up step with a radical, we want to think about what it really means to be a perfect square. So for a perfect square, it means my power is divisible by 2. For a perfect cube, it would mean my power is divisible by 3. For a perfect power of 4, it means my power is divisible by 4. So let's look at the next example that we had written out. So here we're up to cube roots. So we want to ignore the x and the y for a second and just look at 54. I want to rewrite 54 as a perfect cube and whatever's left. 27 is a perfect cube, and 27 times 2 would get me 54. Then I want to move on to the x's. I want to break up x to the 6th as a perfect cube and whatever is left. And if you remember what I was just saying, when it comes to x to a power, in order to be a perfect cube, what I'm actually looking for is I'm looking for the power to be divisible by 3. And x to the 6th is already divisible by 3, so I don't really need to break anything up. I'm just going to rewrite it. And when it comes to the y's, for y to the 8th, I again am looking for a power that's divisible by 3. So I'm going to use y to the 6th as a power divisible by 3. And when I say, hey, what's left? I got y squared left because 6 plus 2 gets me up to 8. So I have y to the 8th. All right. So that's the break it up step. Now let's do the take the radical step. There's 3 things I can take the radical of. The cubed root of 27 is 3. The cubed root of x to the 6th is x squared. The cubed root of y to the 6th is y squared. These are all values that no longer have a radical. Now I can carry down the values that still have a radical. That I had cubed root 2 that didn't simplify any further. And I had cubed root of y squared that didn't simplify down any further. And now comes the clean it up step. And now it's actually really important because that's a mess what we have right now. And what we want to do in the clean it up step is we want to take anything that's not a radical and bring it together up front. So we have 3 x squared y squared. And then we want to take everything that isn't a radical and put it together. Cubed root of 2 and cubed root of y squared become cubed root 2y squared. And now this is a much prettier answer. That's what we mean by clean it up. Let's look at one more example. We're looking at fourth roots now. In the break it up step for 81, 81 is already a perfect power of 4, so there's nothing to break up there. So let's talk about z to the 11th. For z to the 11th, if we're trying to break this up as a power of 4, then we're really saying I need a number that's less than 11 that's divisible by 4, or in other words, a multiple of 4. So one thing you can do on these is just to count by 4s. 4, 8, 12. Oh, 12's too big. Let me go back a little bit. 8. So that's what we're going to use as z to the 8th. And if I've accounted for 8 of my 11 z's, there's 3 of them left. So now the things I can take the fourth root of 81 is 3. The fourth root of z to the 8th is z squared. And I can't do anything with the z cubed. So this is just 3z squared, fourth root, z cubed. All right, so the next type of problem that we're going to be doing are problems that have the following directions. Use the quotient rule to divide, then simplify. Now, those directions seem to be fairly simple and straightforward. Use the quotient rule to divide, then simplify. 8 words. Those 8 words right there give you 5 steps on how to solve this problem. So this problem is not altogether trivial. It's actually a lot of work to get to the answer here. But again, the directions here are going to walk you through how to do that. So I want to walk you through and point out, use the quotient rule is going to tell you to do something. So the quotient rule, remember, is this rule that says if I have a radical of a fraction, I could write it as a radical on top and a radical on the bottom. But that can also go the other way. It can say if you have a radical on the top and bottom, you can write it as one big fraction. And so that's what's going to happen in this case, is we're going to write this as one big fraction. Then you're told to divide. So step 1 was use the quotient rule. Step 2, once you have a single radical, is you're going to divide whatever's going on inside that radical. You have a fraction now. And then the last part of the directions say to simplify. And this is going to be steps 3, 4, and 5 to this problem. And that's going to be break it up, take the radical, clean it up. So again, those 8 words, use the quotient rule to divide, then simplify, are really giving you 5 steps of what to do. And I want you to write those as 5 separate steps as you're doing these types of problems. But again, if you're keeping your note cards, your flashcards, here's another flashcard, and it would be a great idea on one side to put the directions and on the other side to write what those 5 steps are. If you can identify those 5 steps, these problems are not really that hard. If you can't identify those 5 steps, they are very, very hard. Let's actually do this example now. So our first step here is use the quotient rule. So the quotient rule is the rule that says we can write this as one big radical. Now keep in mind that that 5 that's outside the radical is just going to stay there. It's in the bottom, so we're going to write it as 1/5. But we're going to write one big old fraction of 270 y squared over 3 y to the negative 4. That was our first step of use the quotient rule. Our next step is divide. So inside that radical there, 270 divided by 3 is 90. Y squared over y to the negative 4th. Remember that we're going to subtract the exponents. So 2 minus negative 4 turns into 2 plus 4, which is just y to the 6th. That 1/5 is just staying there this whole time. So now going back to my directions, my next part of the directions were simplify, which we know means break it up, take the radical, clean it up. So the 1/5 copies down. For the break it up step, let's take the square root of 90 and break them up as a perfect square and whatever's left. 9 goes into that, leaving us with 10. As far as y to the 6th, that's also a perfect square because remember 6 is divisible by 2. We're not looking at 6 being a perfect square, we're looking at y to the 6th being a perfect square. And as long as that exponent is even, it's a perfect square. That was the break it up step. Now let's do the take the radical step. Square root of 9 is 3. Square root of 10 doesn't simplify, and the square root of y to the 6th is y cubed. Now let's clean it up. How about the things that are outside the radical? We have a 3 and a y cubed on top with a 5 on the bottom. And then things that have a radical, square root of 10. And that's it. So we can see that each step of the way was not that hard as long as we understood what each of those 5 steps were. So again, going back to the top where we had the directions written out, use the quotient rule. That was this step here, where all we did at that first step for use the quotient rule was to write a single radical instead of a radical on the top and the bottom. Our next step to divide, we divided 27 by 3 and y squared by y to the negative 4th. In the last piece of the directions that said simplify, we broke it up as break it up, take the radical, clean it up. Those 3 steps we should have memorized at this point. Break it up, take the radical, clean it up, and we got a nice little answer. All right, we're going to go ahead and change gears a little bit here. This is going to be radical related, or we'll call it radical adjacent. We're going to talk about the distance formula, sorta. We are going to talk about the distance between 2 points. So You may have seen this formula before, that when you're asked to find the distance from some ordered pair x1, y1, and we want to find the distance to some other ordered pair x2, y2, that you might have seen this formula here before, where the distance between those points is x2 minus x1 squared plus y2 minus y1 squared, then take the square root of that. So first thing I want to say before you start jotting anything down there is don't memorize this. There's no reason to memorize it at all. And I'll show you why. I'm going to show you where this thing comes from, because there's a much easier way of dealing with this than to deal with this memorizing of a crazy formula. Because I'm going to tell you, if you try to memorize this formula, you're going to mess up one of the signs. You're going to accidentally add the x's instead of subtract them, or subtract the squares. There's way too many things you can mess up when this is really a ridiculously simple concept. Now, to understand the ridiculously simple concept, we do have to understand either a basic concept of counting, which is the way I prefer you to do this, or at least the basic concept of how to find the distance in one dimension. That if I have the number 2 and the number 10 on the number line, to know what's the distance between them. Well, we could count and say, well, it's 3, 4, 5, 6, 7, 8, 9, 10. And so it's 1, 2, 3, 4, 5, 6, 7, 8. It's 8 units difference. We could do that. Or you could say it's subtraction. The distance in one dimension is accomplished by the use of subtraction. So in one dimension, it's really easy to find distance. Now, the distance formula for two dimensions, when we have an x and a y, I'm going to show you is just a cheap ripoff of the Pythagorean theorem. So if we've got two ordered pairs hanging out there, so let me go ahead and just call one of these guys x1, y1, and the other one we'll put somewhere else. It doesn't really matter where we put it, but we'll call it x2, y2. The way that we can turn this into a cheap ripoff of the Pythagorean theorem is to drop a line straight down from the one and straight over from the other. If we go straight down and straight over, we form a right triangle. And this hypotenuse over here is the distance that we're looking for. And so going back to our idea of the distance in one dimension, note that this ordered pair that's at the 90-degree angle is straight down from x2. So we know we haven't gone left or right from x2, so it's still x2. The y value, it's straight over from y1. We haven't gone up or down, so that guy is y1. So if I want to find the vertical distance here, well, that's a one-dimensional problem. That's just the difference in the y values, because they're straight up and down from each other. And if I want to find the horizontal distance, well, those are just straight apart from each other. That's x2 minus x1. And so if I want to find the distance, I can use the Pythagorean theorem. I could say my hypotenuse squared is just one of the legs squared plus the other leg squared. And if I want to get the d by itself, I would take the square root. And what we're going to see is we're going to get the fancy-dancy distance formula that we have up there. But again, don't memorize this. Once we start throwing numbers into the mix, you can do this every time by just drawing the triangle and using the Pythagorean theorem. Let's take a look at an example of doing that. So in this example, we're asked to find the distance between those two ordered pairs, -3, 7, and 2, 3. So instead of trying to plug into some fancy-dancy formula, what I want you to do is draw a picture. Let's draw a picture of point P, which is -3, 7. There's point P. Point Q is the ordered pair 2, 3. The distance we're looking for is to connect the dots right there. That's the distance we're looking for. So what I'm asking you to do is instead of trying to plug into some fancy dancy formula that you are going to make sign mistakes with, is my suggestion is just draw the picture, create the right triangle. Draw a line straight down from one of the ordered pairs and straight over from the other ordered pair, creating a 90-degree angle. And if you want to use subtraction to find some of the distances that are in this problem, you absolutely could. Or you could just say 1, 2, 3, 4. My height is 4. My horizontal distance is 1, 2, 3, 4, 5. My horizontal distance is 5. I can now use the Pythagorean theorem that says legs squared plus legs squared equals hypotenuse squared. 16 plus 25 equals distance squared. 41 equals distance squared. Take the square root of both sides, and the distance in question is the square root of 41. We had no difficult signs to deal with. We counted. That's all. Now, to fully answer this question, we were asked for a 3 decimal place approximation, so we could go ahead and get our calculator out and say, what is the square root of 41? And remember, if you're using the scientific calculator, you might have to hit that button above enter that has the left arrow and the right arrow together that goes between classic mode and math print mode. But we're looking at 6.403 as an approximation. And the other cool thing about drawing this picture then is that we can sort of look at this and say, does that make sense? If I go 1, 2, 3, 4, 5, 6 plus a little more, sure, it looks like about 6-ish. So obviously that's a really ballpark estimate of just putting some tick marks in there, but we can get an idea of, yeah, this looks like a reasonable answer. Whereas if I forgot to take the square root, for instance, and I said it's 41, I should be able to look at that real quick and say, that is way shorter than 41. So drawing the picture helps you visualize roughly what your answer should be and allows you to count rather than have to worry about subtraction with signs involved. So there you go. That's what I would do if I were you.